Welcome to the functionality of EVPN module. By the end of this module, you should be able to describe EVPN functionality. Virtual Extensible LAN or VXLAN is a Layer 2 or L2 VPN technology that extends an L2 broadcast domain across a Layer 3 or L3 IP domain. VXLAN is commonly used in data center deployments that use an L3 fabric design. For the current list of devices that support EVPN and VXLAN, please refer to the Juniper Pathfinder website as mentioned in the reference links document in the resources section. The needs of the applications that run on the servers in a data center usually drive the designs of those data centers. There are many server-to-server applications that have strict L2 connectivity requirements between servers. A switched infrastructure that is built around Spanning Tree Protocol or STP or an L2 fabric like Juniper Networks, Virtual Chassis Fabric, or Junos Fusion, is perfectly suited for this type of connectivity. This type of infrastructure allows for broadcast domains to be stretched across the data center using some form of VLAN tagging. An L2 fabric, however, has several limitations such as scalability and manageability. Many of today's next-generation data centers are being built around IP fabrics that, as their name implies, provide IP connectivity between the racks and devices of a data center. How can a next-generation data center based on IP-only connectivity support the L2 requirements of traditional server-to-server applications? Within a VXLAN environment, broadcast domains are identified by using a VXLAN network identifier, or VNI. Each broadcast domain within the VXLAN environment is assigned a unique VNI. To forward traffic between remote hosts that belong to the same virtual network, the virtual tunnel endpoints, or VTEPs, must be configured to participate in a VNI domain. Multicast protocols can be used within the IP fabric to propagate tunneled traffic between the VTEPs that participate in the same virtual network. In a multicast signaled VXLAN deployment, a VTEP must be configured to join a multicast group that is assigned to a virtual network. This is a manual, static process. When a new host, physical or virtual, is connected to a VTEP, the multicast group that represents the virtual network in which the new host will participate must be configured on the VTEP. In a dynamic data center environment where virtual hosts can frequently be added, removed, or moved, this process of adding or removing multicast groups from VTEPs can quickly become unmanageable. Additionally, the flooding mechanism used to propagate MAC address information across the network increases processing and network traffic overhead. It requires the implementation and support of protocol-independent multicast or PIM within the underlay network. Ethernet VPN or EVPN is a control plane mechanism for VXLAN environments that leverages the route, advertising, and scale capabilities of multi-protocol BGP or MBGP to propagate virtual network information and MAC addresses. When a host, physical or virtual, is attached to an L2 gateway, the network information such as VNI, MAC address, and so on, associated with that newly attached host is propagated to remote VTEPs using BGP route advertisements. EVPN control module. By the end of this module, you should be able to describe EVPN control in a VXLAN deployment. VXLAN is defined in RFC 7348, Virtual Extensible Local Area Network, or VXLAN, a framework for overlaying virtualized Layer 2 networks over Layer 3 networks, and describes a method of tunneling Ethernet frames over an IP network. RFC 7348 describes the data plane and signaling plane for VXLAN. Although RFC 7348 discusses protocol-independent multicast or PIM and multicast in the signaling plane, other signaling methods for VXLAN exist, including multi-protocol BGP Ethernet VPN or MBGP EVPN, as well as Open vSwitch Database or OVSDB. The RFC 8365, a network virtualization overlay solution using Ethernet VPN or EVPN, covers EVPN as the overlay solution. Although we cover EVPN as the signaling component for VXLAN in this module, It should be noted that EVPN can also be used as the signaling component for both MPLS over MPLS and MPLS over generic routing encapsulation or GRE encapsulations as well. EVPN leverages the scale and flexibility of MBGP to manage and control a VXLAN environment. An EVPN-controlled VXLAN can utilize multiple equal-cost paths for load sharing and redundancy, which provides multipath forwarding over the underlay network. Additionally, it provides the capability of multi-home servers with active-active forwarding. A key difference between EVPN-based VXLAN and traditional multicast-based VXLAN signaling is the manner in which MAC address information is propagated between virtual tunnel endpoints or VTEPs. With EVPN, locally learned MAC addresses are advertised to remote VTEPs by using BGP updates, rather than the multicast flooding mechanisms that are used in multicast signaled VXLANs. This process reduces unknown unicast flooding and address resolution protocol or ARP flooding. Using EVPN as a control plane also provides the ability to implement distributed Layer 3 or L3 gateways, which can share traffic and provide redundancy to the network. EVPN is based on MBGP. It uses the Address Family Identifier or AFI of 25, which is the Layer 2 VPN address family. It uses the Subsequent Address Family Identifier or SAFI of 70, which is the EVPN address family. BGP is a proven protocol in both service provider and enterprise networks. It has the ability to scale to millions of route advertisements. BGP also has the added benefit of being policy-oriented. Using policy, you have complete control over route advertisements, allowing you to control which devices learn which routes. When using PIM in the control plane for VXLAN, it is really not possible to have a server attached to two different top-of-rack switches with the ability to forward data over both links. That is, both links are active. When using EVPN signaling in the control plane, active-active forwarding is totally possible. EVPN enables for VXLAN gateways to use multiple paths and multiple remote VXLAN gateways to forward data to multi-homed hosts. Also, EVPN has mechanisms like split horizon to ensure that broadcast unknown unicast and multicast or BUM traffic does not loop back towards a multi-homed host. This diagram shows how EVPN signaling minimizes unknown unicast flooding. Here, Leaf 3 receives an Ethernet frame with a source MAC address of host B and a destination MAC address of host C. Based on a MAC table lookup, Leaf 3 forwards the Ethernet frame to its destination over the VXLAN tunnel. Leaf 3 also populates its MAC table with host B's MAC address and associates with the outgoing interface. Since Leaf 3 has just learned a new MAC address, it advertises the MAC address to the remote VXLAN gateway, Leaf 1. Leaf 1 installs the newly learned MAC address in its MAC table and associates it with an outgoing interface, the VXLAN tunnel, to Leaf 3. When Leaf 1 needs to send an Ethernet frame to host B, it can send it directly to Leaf 3 because it is a known MAC address. Without the sequence, Leaf 1 would have no MAC entry in its table for host B, making the frame destined to host B an unknown unicast Ethernet frame, so it would have to send a copy of the frame to all remote VXLAN gateways. The EVPN RFC, that is RFC 8365, mentions that an EVPN provider edge or PE router, Leaf 1 in the example, can perform proxy ARP. It is possible that if Leaf 3 knows the IP to MAC binding for host B because it was snooping some form of IP traffic from host B, it can send the MAC advertisement for host B that also contains host B's IP address. Then, when host A sends an ARP request for host B's IP address, a broadcast Ethernet frame, Leaf 1 can send an ARP reply back to host A without ever having to send the broadcast frame over the fabric. It also helps to enable distributed L3 gateways. Here, host C has a default gateway of 10.1. VPN control plane also helps to enable distributed L3 gateways. Here, host C has a default gateway of 10.1.1.254 configured. Spine A and Spine B are enabled as VXLAN L3 gateways. They are both configured with the same virtual IP address of 10.1.1.254. The spine devices also share the same virtual MAC address. Spine A and Spine B send a MAC advertisement to Leaf 3 for the same MAC. Leaf 3 can load share traffic from host C to the default gateway. Although an automatic virtual MAC address for the L3 gateway is generated, it is recommended to manually configure a virtual MAC address for the integrated routing and bridging or IRB interfaces.